All right. I think we're at the top of the hour, and why don't we get started? Good morning, good afternoon, good evening, kind of everyone, and welcome to the Security Area Advisory Group meeting. This is session one that we're holding now. My name is Roman Daniliou. I'm one of the SecADs, and my co-SecAD is Ben Kadick. Ben, if you want to turn on your video. All right, if we can go next slide, please. So two things we want to talk about before we really get started. Mohit, are the slides flipping or is this an artifact? Perfect. Thanks. So there's two things we wanted to talk about. Of course, we have first the Notewell, which covers the various policies and procedures related to how we do work here at the IETF. If we could flip to the next slide. But in particular, what we want to do is call out one of those things from the Notewell, which is our code of conduct. And so this is really a reminder, as documented in RFC 7154, that we extend a courtesy and respect to our colleagues, that when we talk about things, we focus on the technical bits of it, not necessarily the messenger and the particular individuals involved. So let's not kind of focus on the person, let's focus on the tech itself. And just a reminder that we're all coming actually from different contexts, different kind of perspectives. So remember that assumptions about what operational environments or the technical environments may actually be different than what you consider that particular kind of environment. So please do give the benefit of the doubt to different participants. Next slide, please. So you'll notice in the agenda here and on the 112 schedule that we're doing something different than what we usually do. We like to have Sec Dispatch early in the week. We like to have SAG a little bit later in this week. But to accommodate different kind of presenters, we're doing a hybrid here, so a split session. So the first hour of this meeting is going to be focused on SAG. The second hour is going to be Sec Dispatch, and on Thursday we're also going to split the time. SAG will take the first hour, and if Sec Dispatch needs it, we're gonna have them in the second hour. So the agenda roughly kind of splits like this, where today, in continuing largely on the conversation we had at the last IETF meeting about what post-quantum cryptography agility would look like, last time we talked a little bit about what we would be doing in the IETF. This time around, graciously, NIST, specifically Dustin Moody, who's the post-quantum cryptography project lead at NIST, has agreed to come here to tell us about where that kind of project stands. And we have some time for some open mic. And then on Thursday, we're going to do all the different administrative kind of activities, talk about working group reports, the AD reports, and other topics. But thank you, of course, to the working group chairs who have set updates preparing for that this morning. We're not going to do any agenda bashing here. We're going to save that flexibility for Thursday. You know, today we just really are going to focus on our invited talk. So kind of with no further ado, Ben, unless you would like to add something, let's kind of move over to Dustin. Okay, thanks so much. The floor is yours, Dustin. We're going to flip to your slides now.
Okay, thank you very much. I appreciate the invitation to come and speak here to the IETF. Hopefully you're seeing and hearing me. Not seeing my slides yet. Hopefully you'll get them in a moment. So I plan to talk for about 30 minutes or so and leave plenty of time for questions at the end. So I know that there's lots of things you might want to ask. So again, yeah, I'm Dustin Moody from NIST. And NIST, as you probably are very well aware, is leading a post-quantum cryptography standardization project, which we're nearing the end of. And that's what I will be speaking about today. Next slide. So the motivation is probably pretty clear. It's well known that there are quantum computers that are actively being researched and built, that if they are constructed to a large size where they can do pretty good computations, that these quantum computers would have a noticeable impact on cryptography. And we've seen in the press over the past few years progress being made. There are certainly still challenges to be overcome. It's not an easy problem, but quantum computers, if they are built, they will be sufficiently powerful to give us computational power for certain problems. They won't solve every problem that we want to tackle, but they would give us a lot of very good applications in science. Okay, let's go to the next slide. So at NIST, the threat to cryptography is what we're focused on. It's well known that Shor's algorithm, it's been known for a couple of decades, would break the public key crypto algorithms that we use today commonly. That includes algorithms like RSA, ECDSA, the elliptic curve Diffie-Hellman, finite field DSA. And these are standardized in 3 of our documents at NIST, SP 856A and B, which deal with key establishment and public key encryption, and then FIPS 186, which is our digital signature standard. So if a quantum computer comes online, it would completely break those standards. We'd need to completely just remove them and get new algorithms. So the threat is to public key cryptography the most, and that's where the focus of post-quantum cryptography is. Quantum computers would also be able to impact symmetric key crypto. So we have various symmetric algorithms like AES and SHA-2 and SHA-3. But the effect would be a lot less dramatic. Grover's algorithm would give you a polynomial speedup, not an exponential speedup. But we could handle that by increasing key size, using longer output from the hash functions. So we wouldn't need to completely scrap the algorithms. We just need to change how we use them. And that's easier to handle than coming up with new algorithms. So next slide. So there are many names given to this area. Sometimes it's post-quantum cryptography. It's also called quantum-resistant cryptography, quantum-safe cryptography. But the idea is that we're looking for crypto systems which will be implemented on our current classical computers, because that will still be what everyone is mostly using. But they need to provide security against attacks from both classical and quantum computers. Now, quantum computers, there is progress being made, but they're not yet here. So we may ask the question, why do we need to worry about this now? And there's a simple explanation from Dr. Michele Mosca that explains why there's a threat now, even if we do not yet have a large-scale quantum computer. And the idea is kind of there's a harvest now, decrypt later threat. That your adversary could be copying down your data and it's encrypted and you can't read it right now, but he will wait until there's a quantum computer that comes along and then he'll be able to get access to it. And this little equation, if x plus y is greater than z, helps you measure that risk. If x is how long you need your data to be protected, and y is how long until we have post-quantum algorithms standardized and widely implemented and adopted, and if z is how long until there's a quantum computer, well, if x plus y is greater than z, they will decrypt your data and you will not be providing the x years of information security that you're hoping for. So you can put in what x and y and z are for your particular organization, your application, to see if you could be at risk already. Being in standards, we know that y is not as small as we might hope. Y is more likely going to be 10, 15 years to get good standardization adopted. We've seen that in the past with crypto transitions. X will depend on your organization, the application. Could be due to regulations where you've got to keep health information private or you're protecting financial data. If you're worried about national security, X could be really long, like 30 years. So it's important to have an idea of kind of what Z might be then. So if we go to the next slide, there are various experts around the world who were surveyed in this quantum threat timeline report that was done by the Global Risk Institute that tried to give an idea of when quantum computers that would be big enough to break public key cryptography could be around. Of course, it's an open research question, so nobody knows for sure, but they surveyed 44 experts in the field and asked them, what is the likelihood in 5 years, in 10 years, in 15 years that we would have a big enough quantum computer that would break the public key crypto that we use? This chart is it summarizes their findings, although you need to go to the full report to see all the details. You can see in 5 years, a majority of those surveyed thought there was a pretty little risk. less than 1%, or at the most maybe 5%. If you start going down further, at 10 years, at 15 years, we start to see that there's almost half of the people surveyed were starting to give a fairly significant probability that we could have a quantum computer. So in terms of managing risk, we can see that maybe 10 years, 15 years, and in their opinion, certainly by 20 years, this is something we need to be working on today and seriously considering. Next slide. So to just be clear, sometimes when we're talking about cryptography and quantum, there's another side of the coin that is mentioned, and I want to make sure that you're clear that that's not what I'm talking about today. Quantum cryptography, also the term QKD or quantum key distribution, is using quantum technology to build crypto systems. And there's some pretty interesting things that can be done here. You can actually get theoretically unconditional security that's guaranteed by the laws of physics. There are some important applications where this might be the right solution, but this is unlikely to be what is widely used on the internet. The way it is right now, it's not very scalable. It's very expensive. You need special hardware. You can do encryption, but not authentication. So this is not what our focus is on right now in this project. We do have people at NIST looking at this, and other researchers around the world are as well. But our post-quantum cryptography project is on looking for classical crypto systems to replace the ones that would be broken. Go ahead, next slide. So NIST has been looking at this for over a decade, but it was around 2016 that we began to take some concrete steps in this project to get standardization happening. So we first published a report and announced that we would be doing a large international competition-like process similar to what we've done in the past with AES and with SHA-3. So we put out a call for proposals, we put out our evaluation criteria, and then we gave submitters plenty of time to design their algorithms. We received 82 different algorithms, of which 69 met our requirements and were accepted into the first round. And since then, we proceeded through a number of rounds where during a round that lasted about a year and a half, we would evaluate the candidates. Internally, we would look at them, as well as the cryptographic community around the world as well, looking at their security, their performance, and so on and so forth. At the end of each round, we would select the most promising ones to move on for further study. So we went to a second round, and then we went to a third round, which is where we are now. At the end of each round, we issued a report explaining our decision, and in each round, we also held a workshop where submitters could come and talk about their algorithms, and other research that's relevant could be presented. So I'll talk about this in more detail as we go on, but this is kind of the overall timeline of our project in the past few years. So the criteria that we announced we would be using to judge these algorithms, number one is security. We need these to be secure against both classical and quantum attacks. And security is the most important criteria. That said, it's not always easy to measure security in a concrete way, especially against quantum attacks. Quantum computers are not yet built. We don't know how expensive they'll be to run. We do not know how fast they will be to run. So we have to make some guesses and some extrapolations, and there's some uncertainty built into that. We designed 5 security categories so that submitters could give us parameters to tell us how much security their algorithms would be providing with certain parameter sets. And we related this back to the amount of resources it would take to break some of our symmetric key algorithms. Kind of an unusual way to define it, but this is kind of what we came up with at the time. Level 1 meant that your algorithm was providing as much security, it would take as many resources to break it as it would take resources to break AES doing an exhaustive key search. And then we went on from there, levels 2, 3, 4, and 5. We think levels 1, 2, and 3 should provide enough security for the next several decades, and we have levels 4 and 5 for very high secure needs. Besides security, performance is obviously very important. If things are too slow or too large, we won't be able to use them. So we would measure performance in a variety of different platforms, both on software, hardware, small devices, and so we could see the comparisons between the different algorithms. As we'll see, there's not one silver bullet that is just magically the best in all different categories. We also asked that submitters talk about other properties, and that we would evaluate the algorithms on these as well. As much as possible, we hope for a drop-in replacement. We want perfect forward secrecy, resistance to side channel attacks. The simpler, the better. It's easier to analyze, and less likely to make mistakes when implementing, things like that. Okay, next slide. So we had submissions from around the world. There was several hundred submitters that were involved with the algorithms, and if you put them on a map, they were from all 6 continents and over 25 different countries around the globe. So that was nice to see that we have a worldwide effort going on here. Next slide. In summarizing the first round, so we had a lot of algorithms that we published on our website. We put their specs up. We had the code there so you could download and implement them. There was a lot of schemes that were very quickly attacked. Cryptographers love trying to break new things. And of the 69, I would say in the first month or two, probably about 15 to 20 of them had attacks that severely weakened or broke a lot of those schemes, about 15 to 20 of them. We also noticed there was a lot of very similar ideas in what was submitted to us, particularly in looking at lattice chems. So we asked for public key digital signatures, and the other category we asked for was public key encryption, or equivalently key encapsulation mechanisms. And in that table down in the bottom right, you can see kind of the categories of the type of algorithm, as well as the mathematical primitive that was based on. And we had the most that were based on lattices and codes for chems. We held a workshop where the submission teams were invited to come and present their algorithms. Had a lot of discussion there, a lot of good attendance there. That was held jointly with the PQ Crypto workshop. We established an online message forum called the PQC Forum, where we could keep track of comments about the algorithms. People could ask questions, discuss research results. That forum continues today and is an active area where there's a lot of discussion going on there. And in the first round, we started to get research and the first performance numbers as well, so we could start evaluating these schemes. After a year, we made some hard decisions and we selected 26 of the schemes to move on into the second round. So next slide. Also going on into the second round, we encouraged some submissions to merge that were very similar. And we saw some four different mergers continued on, and they all advanced into the second round. The idea with the second round was that we wanted to maintain the diversity of algorithms, but select the ones that were most promising. So we still had a number of lattice-based, code-based, multivariate signatures, and so on and so forth. The second round was a lot like the first. Cryptanalysis continued. Some algorithms continued to get broken. We held a workshop, more research. After 18 months, we had 15 submissions that we picked to move on into the third round. And we can go ahead and we can go to the next slide. So there were some tough decisions here. If you've been following the process, you can see some of the submissions that were on the left. These were the round 2 algorithms, and we maintained the diversity going on into round 3, showing our categories for encryption in chems and for signatures. They're kind of color-coded according to the mathematical primitive they're based on, so you can see that diversity was preserved. And in looking to see how we're going to make our selections, this could kind of help provide some understanding as to how we'll do that, where we try and again keep algorithm diversity, but select only the ones that appear to be the best of each type. Okay, let's move on to the next slide. So currently we are in the third round. We've selected 7 finalists and 8 alternates. The finalists are the algorithms that we feel are most likely to be ready for standardization at the end of the third round and would fit the most general purpose applications. The alternates we are still interested in, but they would most likely need a 4th round of study. Some of these were selected as kind of backup candidates if there were research results, or for certain performance applications. Some of these algorithms were suited for, the performance was tailored that they might be appropriate for one application, but maybe not as good for general purpose use. The chem finalists that we had were Kyber, Entru, Sabre, Classic McLeese, and the signature finalists were Dilithium, Falcon, and Rainbow. And then the alternates are listed there as well. So we can go to the next slide. So if we look at the lattice-based chems, 3 of them were selected as finalists, Kyber, Sabre, and Entru. All 3 are good all-around candidates. Their key sizes are pretty good. Their efficiency and implementation is quite good. Kyber and Sabre are a little bit more similar. Entru is based on a slightly different problem, but all 3 we selected as finalists. We had Entru Prime as an alternate, and FrodoChem was also an alternate. FrodoChem made a security performance trade-off where they were a little bit more security. They did not use structured lattices, so the key sizes are a little bit bigger. Performance is a little bit smaller, but potentially it provides a more conservative security option. Okay, next slide. In looking at the remainder of the chems, 3 of them were based on codes. Classic McLeese, which if you've been in cryptography, you've heard that before. It's been around for a long time. It was selected as a finalist. Very large public keys, very small ciphertext, very efficient. So for some applications that would work well. Bike and HQC introduced some structure to get the public keys down a little bit smaller. We're very interested in having another general purpose chem based on codes. Bike and HQC look like good candidates. So we will likely go to the 4th round to see if either of them will be standardized. And then we have Psych, which is based on isogenies of elliptic curves. Very small keys, but it's a little bit slower than all of its competitors. Next slide. So here's a couple of charts just to show you kind of the different key sizes that we're looking at. And to some extent, this is informed by the mathematical primitive that they're based on. Do note that on the axes, these are logarithmically scaled. You can see that the orange one, Psych, has the smallest key sizes, and then the lattice-based algorithms, and the code-based algorithms, and then Frodo, that blue dot up in kind of the top, is up there. And the gray dot in the far right is Classic McLeese with very large public key, very small ciphertext. Okay, next slide. If we want to look at the efficiency, this is just to give you an idea of the order of magnitude. Performance will be based on, what platform you're implementing it on. Again, note that the cycle counts on the left here are in a logarithmic scale. And you can see that some of the best performance numbers we're getting from our lattice chems, Kyber, Entru, Sabre, Entru Prime. And then you can see the code-based ones a little bit slower. And then Psych has slower keygen and caps and decaps than a lot of the other algorithms it's competing against. Okay, next slide. So if we look at the signatures, we have 2 lattice-based signatures, Dilithium and Falcon. Again, both are very balanced. They're very efficient. They were selected as finalists. We had 2 signatures that were based on symmetric key primitives. We have Sphinx Plus, which is very stable. Its security is very well understood because it's based on the security of hash functions. It's a little bit larger and slower than Dilithium and Falcon. Picnic, very novel design. So we're still looking at that. And then we had Rainbow and Gems that were multivariate signatures. They both tend to have large public keys, very small signatures. Pretty efficient at verifying in particular. However, during the third round, there's been some cryptanalysis results that have attacked both Rainbow and GEMS and call into question their security for both those algorithms. If we go to the next slide, we can look at a couple of charts to see kind of the sizes that we're looking at for them. Again, logarithmic scale for the axes. We can see that Picnic and Sphinx Plus have very small public keys, very large signatures. The gray multivariate, very large public keys, small signatures. And the lattices kind of middle ground where they have key sizes and signature sizes on the order of 1,000 bytes, roughly. Next slide. If we look at a chart to look at performance, again, logarithmic scale and the cycle count, we can see that each of these algorithms has different kind of performance areas where they tend to do a little bit better. Some have better key gen, some have a slower key gen, some verify very much faster. So we can see kind of different comparisons there. Okay, next slide. So our timeline, we have been in the third round for over a year, and it will end roughly the end of this year, start of next year. Right now, it's looking probably more likely it will be the beginning of 2022. And that is when we will announce which finalist algorithms that we will standardize. We've also previously mentioned we may potentially standardize Sphinx Plus, even though it's an alternate, because we want to make sure we have more than one signature algorithm. And we had dilithium and Falcon. We expect to choose one of those algorithms. The multivariate signatures, we had some attacks on them. So that is why that might be something we do. Again, we want these algorithms to include, or these algorithms that we announce to include solutions that can be used by most applications. So that's what we're targeting at the very first especially. We'll also issue a report to explain our decisions, and we will announce any candidates that we want to advance to a fourth round to continue to study in a fourth round for potential standardization. These algorithms that we announce at the end of the third round, we will work with the submission teams to create draft standards that we will put out within probably ought to take us a year or so to get public comment. We will address those comments and hope to get the first set finalized, published by 2024. Okay, next slide. So I talked about the signatures. We have a lot more chems and different types of chems. In signatures, we have a smaller number. So we're going to introduce at the end of the third round what we're calling an on-ramp for new signatures. We will issue a new call for signatures that we want designers to design for the future. We'll announce a submission deadline. We'll give designers probably 6 months to a year. This will be a much smaller scoped project than what we announced 5 years ago. We're not looking to get 60, 70, 80 new algorithms. We want a very small number. The main reason is to diversify our signature portfolio. We're happy with the general purpose digital signature schemes that are based on structured lattices. That would be dilithium and Falcon. But we also want another general purpose algorithm that's not based on structured lattices. The other ones that we're still in the third round, they're a little bit bigger or slower in some areas. So that's our primary target that we're looking for. We might be convinced to be interested in some signature schemes that target certain applications. For example, if there's a scheme that has very short signatures, that could be something we're interested in. Of course, the more mature the scheme, the better, and we'll decide when we see what gets sent in, which, if any, of the schemes that we want attention focused on. So next slide. How are we making our decisions? Well, right now we're already meeting to begin our process to select the algorithms. We're meeting frequently. We're comparing the algorithms. We're taking a detailed look again at their specifications, what's happened during the third round, new research results, new performance benchmarks. But we're trying to just follow the evaluation criteria that we announced. We said security was number one, then performance, and then some of these other algorithm and implementation characteristics. For the lattice chems, our main decision will be selecting an algorithm from Kyber, Ntrue, and Sabre. All three are based on structured lattices, have similar performance. There are some differences, and that's what's making this a hard decision. For lattice signatures, our main decision will be looking at dilithium and falcon. Our other choices, they'll mostly be made on an individual basis. If we standardize classic McLeese, it's kind of competing against itself, and so on with the other algorithms. Next slide. One issue that's proving to be very important is patent and IPR issues. And this is a very complicated area. Our team is mostly made up of mathematicians, computer scientists. We are not lawyers, so we don't understand all the IP issues. But we acknowledge that the impact of IP can be very, very important on adoption of these algorithms. Each of the algorithms, their submission teams, gave us signed statements indicating any patents that they had on the algorithms. But there's an issue that's arisen with patents from third parties that are not the designers of the algorithms. NIST is actively engaging to resolve the known issues that we're aware of. When we have something concrete, we will share it. We want to make very clear, though, it may not be possible for us to resolve all the IP issues. We can't control what outside parties do completely. And IP is a legal issue, and it's not to be decided based on what I think as a mathematician. So in light of the above, we think that the discussion is best focused on the impact of IP. How will that affect adoption, and how should we factor that into our decision-making process? We very much want to select algorithms that will be widely implemented and adopted, and we know that having any patent or IP significantly affects that. And we want to have standards that are freely available to everyone to use. Next slide. So there has been some work done already on stateful hash-based signatures. The IETF has 2 RFCs that standardized XMSS and LMS. Based on those, NIST also issued a standard SP800-208 that has stateful hash-based signatures. Want to caution, these are not general purpose digital signatures. You have to carefully manage the state, otherwise you can completely blow your security. So all of these documents include guidance on how to safely do this and which applications this is appropriate for. But wanted to make sure you were aware of hash-based signatures. Okay, next slide. As we look towards the transition, one thing that's being discussed is a hybrid mode, and that's where you use a classical algorithm and a post-quantum algorithm in some combination where you're relying on the security of both algorithms. And this is a potential approach for migration that many people seem to be interested in. NIST allows this in one of our documents. You can combine a shared secret derived from a current NIST standardized algorithm with a shared secret derived from some other way, i.e. a post-quantum algorithm. You concatenate them and run them through a KDF, and you can still get FIPS approval on that process as explained in that document. So we know that there's going to be probably continued discussion on the best way to implement any mode where you're combining algorithms. NIST hasn't really taken a position on the best way of how to do this. We think it certainly is an option to consider. You take a performance hit, but it's perhaps a good way to transition into the future and getting used to these post-quantum crypto algorithms. So let's go to the next slide. NIST will issue guidance on the transition to post-quantum algorithms. We don't yet have algorithms announced, so we cannot give that guidance yet. But we've previously given crypto transition advice, and we will do so here. So let's go to the next slide. In working with the NCCOE, the National Cybersecurity of Excellence, we also have a project that's focusing on the transition and migration to PQC. So this project is being run by some of our colleagues in the NCCOE, but we're participating with them in this process. They've held a workshop. They've finalized their project, so you can go to their website. Most recently, they announced they published a Federal Register notice where you can join the project and participate in this process. So I'd encourage you to go to the project webpage if you're interested in learning. They also have white papers on how an organization can start preparing for this transition. And this is an important effort to help us get ready what we can do now before the standards are announced and before the final standard is published. Okay, next slide. These are some of the things that organizations can do now. It mostly involves taking a look at the cryptography you're using now, seeing what public key algorithms you have, looking at how you can transition out of them, how you can swap in new algorithms. That's often called crypto agility. And then just making sure that your staff is aware of this. You've got someone tasked with having a plan for making the transition to post-quantum algorithms and tracking developments in quantum computers, in standardization projects. You could test out some of these algorithms to see how will they meet, how will they fit in your applications. But we'd encourage you, the sooner you plan ahead and prepare, the better it will be for you. You'll make less mistakes. It'll be less disruptive, less expensive as you do that. So next slide. So in conclusion, we're getting near to the end of the third round. We can start to see the light at the end of the tunnel. NIST is grateful for everybody's efforts, the cryptographic community, researchers, industry who's tested out these algorithms, other standards organizations who are working as well to help create strong post-quantum crypto standards. And we'd encourage you to check out our webpage, sign up for the forum if you haven't yet, and you can always contact us directly if you need to. So with that, I'd be happy to take any questions that you have about our project.
John, please.
How many changes or how little changes can we expect from now until the final standards are ready, hopefully in 2024, which is like 2-3 years from now?
Okay. Yeah, so at the end of each round, we allowed each of the algorithms that advanced on to make minor tweaks, not major redesign. So we expect that at the end of the third round, if we select an algorithm, we would work with the team and allow them to make any minor tweaks from things they've learned during the third rounds, but nothing major, no big redesigns. So I would say that the type of changes would be similar to what you saw at the end of each round when teams made tweaks.
Watson, I think you're up next.
Cover. So one of the things that happened with elliptic curve cryptography is there was a very long gap between NIST standardization and adoption, and that was partially due to IPR concerns, and some operating systems really didn't have any support for quite a long time because of these IPR concerns, as well as performance issues. And then when further developments resolved those performance issues, NIST didn't respond. And it's not until 2 years really that NIST has said that, oh yeah, we are going to standardize faster elliptic curves. And my concern is, has NIST is with post-quantum, where we have possibilities, especially in signatures, of faster and better algorithms coming out, is NIST going to be more responsive? Or is it going to be a situation where we're going to be stuck for a while with things that maybe we can't do everywhere and we really need to, because NIST isn't paying attention anymore to what's going on? They say, okay, we've got the spec and we're done.
We expect our post-quantum work to continue on into the future. At the end of the third round, we're announcing these algorithms. We will get a first standard out, but the project will continue on. There's going to be a fourth round. There's going to be the on-ramp for signatures. So to the best of my knowledge, yes, we will be looking for the future research and being proactive. And if we need to, make changes or standardize new things, that we would be responsive.
Phil, go ahead.
Yeah, Great talk. I've got to ask about threshold. Can any of these be adapted to a threshold version?
It's possible that some of them could. As they currently are in the specs right now, I'm not aware that any of them have a threshold implementation. And that's not our primary focus. We first want to just get an algorithm standardized so that people will have it and begin to get using. And that could be future work where there could be threshold versions of these done. Are any of them particularly suited where they'd be able to, they look like they could allow that? Some of the lattice-based ones, potentially. I think, if I'm remembering, Lima was a first-round lattice-based candidate, and it talked about how it could be done in a threshold way, potentially. So that would be where I would guess is the lattice-based ones might have the easiest way to do that, but I'm not currently aware that anyone has done it yet.
Okay.
Ecker, you're at the top of the queue.
Yeah, thanks for the talk. Much appreciated. I noticed that you're standardizing chems, and but a lot of our protocols really want Nike instead. I know there's sort of a dearth of algorithms there, but is NIST planning to do anything to try to like foster that work?
Well, back at the beginning when we were first starting this project, that's what we were hoping for, was kind of a direct analog of the Diffie-Hellman. Looking at the submissions that came in, there was none that really provided that at the time. I think there have been some ideas that are out there right now that could potentially do that. But I think our feeling is we think that you can use the chems and you can modify them to get what you need done still. If we do see a really good one coming in the future, we could work on that, but we don't have any current plans at the moment to focus on that.
Oh, okay, it is true you can use the chems for that, but it is not convenient. So it would be much more convenient to something that looked much more like Diffie-Hellman.
Yep, we understand. Yeah.
Hi, I guess partly repeating what's said earlier. I mean, encumbered outcomes would be a really bad outcome, I think, for this. I know you can't control that. Also, though, I think the thing you can control are the number of options. So I know that you're not liable to pick one single algorithm and declare a winner, but I hope for each algorithm you don't declare 75 different options, and then that would cause a lot of work in an organization like the IETF, where people then have to decide which of the 15 options do they winnow down to 10 and then to 1 and so on. So I'd encourage you to the extent possible to reduce the number of outcomes to the absolute minimum you can.
Thank you for that suggestion. Yeah, we've heard that feedback from industry as well, and that's something we plan on doing. We will standardize more than one, but we want to keep it as small as possible. Yes.
Hi, Ben Schwartz of Google. I wanted to ask if you and the whole group at NIST had given much thought to combine schemes that combine one of these signature algorithms with a Merkle algorithm to amortize the signing costs. There's a draft in the TLS working group right now, adopted draft on batch signing using Merkle trees to share the cost of a signature across a large number of handshakes. I wonder if that influences any of your thinking.
Yeah, that would fall into our third evaluation criteria, kind of the algorithm and implementation specifics. Yeah, we are aware of kind of research being done in that way, and if an algorithm allows for, batch signing in a particularly efficient way, that would be a plus for it. So we do try and be aware of that and factor it in when we're going to select something. Yes.
Okay. Yeah, just because in general it seems like slow signature schemes with small signatures could easily be combined, sort of trivially, with the old-fashioned Merkle signature trees in that situation.
Yep, and that would be a good way to get some algorithms that might be a little more cumbersome to be able to be used. Yes.
Okay, great. Thanks.
Hi, Ben Kadek. So there was a topic that came up in the chat a couple times about sort of key sizes, and I know you had, I think, a little bit of data in the charts about key sizes, but like, is there some minimum expansion factor that we're going to hit when in key size when we go to the post-quantum algorithms?
Well, the main ones, the finalists that we're looking at right now, the structured lattice ones, for chems, they're roughly about, for category 1, 1,000 bytes. That's the smallest we're seeing for good general purpose algorithms. Psych does have smaller keys that are a couple hundred bytes, but then its performance is an order of magnitude slower. I'm looking at the signatures. Falcon is smaller than dilithium for sure. It's less than 1,000 bytes. Dilithium's more like 1,500, 2,000 bytes for category 1. So based on what we have, that's the best we can kind of do coming out of round 3 at this point.
Sure. Yeah, we're going to have to take what we can get, at least at the start. All right, thanks. And I guess, Mike, you are next in the queue.
I remember at the Florida iteration of this conference, there was a proposal around hybrid schemes. I think it was sort of flippant, but the proposal was we might be able to achieve a security level by combining 2 smaller, faster things into a single primitive. Do you remember that idea floating? Has there been any traction? Like, did that idea die? I know it was a joke, but it sort of seemed maybe worth pursuing.
I don't remember that from the Florida workshop. So I'm not remembering it, which makes me think I mean, maybe there's been some efforts in that direction, but I'm not aware of them. So I don't know.
Okay, so that's the end of the queue. Are there any other questions for Dustin? I am not seeing anyone join. So Dustin, a profound kind of thank you for joining us and giving us an update for what NIST is doing. This is kind of such an important kind of activity for our future roadmap. So again, if we have any other questions, we may kind of follow up with you. But again, kind of thanks so much, and have a good rest of your day.
Okay, thank you.
All right, so we have ended early. We have about 10 minutes officially kind of on the schedule before we pivot to SecDispatch. So opening the mic, kind of open mic for SAG topics. And after we drain that queue, we're just going to pivot on to starting with the SecDispatch meeting. Would anyone like to join the queue for open mic SAG? Florence, please.
Hi, Flo from UK NCSC. I was wondering, kind of picking up on something we discussed at the last SAG meeting, there was some chat around kind of coordination of post-quantum work in the IETF. And it seems from the mailing list that that's kind of been turned into the discussion around the PQ maintenance group, which sounds great. But I was wondering if there's any plan for coordinating the post-quantum work between different groups. So the stuff that's going on in different working groups.
I would say from at least kind of the AD perspective, we are just informally doing that formal class of kind of coordination. If we end up with a working group to do that, we would hope that that entity would roughly kind of take the lead. So that class of coordination is kind of on, in the kind of thinking, but right now this is roughly just informally done. The 3 places, at least in SEC, that we have actively chartered items are LAMPS, TLS, and IPsec. I'm sure more work is needed.
So do you think some of that coordination could end up taking place in the kind of PQ agility, PQ maintenance group, or is that not on the cards for that group? Thank you.
I think that's up to what the community actually wants. The way that post-quantum, that particular charter, that particular thing we're having on the mailing list, kind of talking about that agility work group is largely to catch orphans. So it's focused on what are protocols we may need to touch that don't have existing working groups. So if there is existing work, for example, kind of in TLS or kind of IPsec, it's probably going to be handled out of that working group, which is not to say, the topic can't be coordinated, but that work is likely going to be in that working group, at least as the text is currently written. The other thing that working group, that kind of proposed kind of template working group that we're talking about might have is the ability to kind of generally talk about things before that we know some organic coordination baked in there, yes.
Thank you.
Great, thanks. Anything else related to open mic for SAG? Okay, so I'm not hearing anything, so we're going to close the open mic line and metaphorically close the SAG portion of this meeting and turn it over to our SEC dispatch chairs. Mohit, I'm jumping in here. I think you're talking, but I at least can't hear you.
Apologies for that. Hopefully you can hear me now. So I was just saying it's afternoon here in Helsinki, so good afternoon, evening or morning, depending on your time zone. I guess, Roman, Ben, we can just start with SEC dispatch. We don't have to wait for another 8 minutes to meet the hour. Hopefully that's fine.
Yeah, absolutely. Please continue.
Yeah. So welcome to SEC dispatch at IETF 112, and we have our ADs and my co-chairs Richard and Kathleen who will be helping me today. So welcome. I'm trying to arrange the slides from here. So you have already seen the note well once, and it still applies. It hasn't changed. You're still in an IETF meeting. Hopefully you're familiar with most of the BCPs, but if not, you can have a look at them. They're listed here on the slide. Please go and have a look at them. It's anyways good to refresh your memory once in a while. Perhaps we would like to emphasize the IETF code of conduct still applies. So you just saw this when Roman was presenting the slides earlier, but again, to re-emphasize, have a look at RFC 7154. Please respect your colleagues and try to be as impersonal as possible in discussions. And yeah, we are trying to make the internet better, so let's be good to each other while we do that. So this session is being recorded. If you were not aware of it so far, you were being recorded in the last 1 hour, and you will continue to be recorded for about a little over the next hour as well. And headsets are recommended. State your name before you speak in the mic queue. All right, here's some links. So very importantly, we'll be using the notes.ietf.org for notes, and we'll be using the SEC dispatch link, not the SAG link. I think my co-chairs will manage the Jabber, but we will need note takers. So I wonder if we have someone helping with the notes already. Oh, I see. At least for SAG, someone was taking notes, probably Roman, but it would be nice if someone can take notes for SEC dispatch as well. Do we have any volunteers? I don't see anyone on on the chat. I would love to, but I think I'll be switching slides from here and managing other things. So, okay, thanks, Jonathan. So we'll have note takers. With that sorted out, before we get to the actual agenda, here's a quick reminder of what is SecDispatch and what do we do. So SecDispatch is mostly for recommending the next steps for new work. It does not adopt drafts. We could direct the new work to an existing working group. We could suggest a new working group, whether that is through a BOF or not, depends on the ADs. We could also ask our ADs to sponsor some documents or then come to the conclusion that IETF should not work on a particular topic. Yeah, hopefully you're familiar with these buttons by now. I don't think we need to spend much time on this slide. FYI, so before we get to the agenda for SecDispatch, there was a draft presented on secure credential transfer in the dispatch session earlier this week. So yesterday there was a draft on secure credential transfer that was presented, and the outcome is on the dispatch mailing list. Kirsty has thankfully given us a heads up so that we can also inform the security community in this meeting in SecDispatch. The full outcome is on the mailing list, but I anyways wanted to provide a heads up that there will probably be a BOF. At least there was consensus in the dispatch working group to initiate a BOF on this topic, and I'm sure like this is of interest to many of those who are attending the SecDispatch. So do have a look, follow what's going on, and we might have a BOF before or during the next IETF in 2022. With that, we are now at the agenda for this session. Thankfully, we managed to finish the administrivia before the hour, so we are in good time. We'll have a presentation from Tommy on private access tokens, another presentation on security and privacy considerations for multicast transports from Jake, and then we'll one of the chairs will summarize the outcomes at the end of the session. We already have Jonathan. Again, thanks for helping us with the notes. We have scribes in place. Is there anyone who would like to bash the agenda? If not, in that case, I'll share your slides, Tommy.
Yeah, actually, if I could share my own slides, I can just ask to do that. That would be great.
Yeah, that's fine. That's fine.
And then as a minor agenda bash, I know that there also is time on Thursday, so I guess if we are having discussion, I assume we have probably a little bit more than 25 minutes for each of these talks that we could probably go into.
Sure. Yeah.
All right. I'm asking to share slides. If you could approve that. Thank you. All right. Good morning, good afternoon, everyone. So I'm Tommy Pauly, and I'm going to be presenting on behalf of several co-authors I have here. I'm from Apple. I'm also working on this document with Chris Wood, who's at Cloudflare, Johnny Angar from Fastly, and Stephen Valdez and Scott Hendrickson, who are at Google. And this is a document that we are calling Private Access Tokens. I sent it out to the list a little bit ago as we publish on the day of the deadline, but we want to share that with you here and see what the next step for this type of work is. All right, so just to give you an idea of what we want to go through, first we want to talk about the motivation for why we think this is important work to do. We're going to briefly go over what the protocol architecture is without diving into all of the details. If you want to see that, read the document. And then lastly, talk about some deployment considerations before we get on to the dispatching questions. All right, let's go. What problem are we trying to solve here? Okay, so let's tell a little story. So servers, as we know, often use client IP addresses as an identification mechanism. And this is because clients generally just tell them, hey, when I'm connecting to you, here's my IP address. You can know who I am. And this is useful. And amongst other things, servers can recognize these addresses over time. And some of these are useful features, like they can use it to rate limit access to some particular resource when that's appropriate. And the origin can say, oh yeah, this is the 5th time I've seen you today or this week. Sometimes that's a good thing. For example, there are services that want to be able to have, oh, here's a metered paywall of you get 7 free articles. And if I can see this, you get the free articles. I'd like to point out that it's kind of hilarious that Wikipedia, for their metered paywall site, had to come up with an entirely fake newspaper here. Now, there are problems, many problems with using IPs for tracking like this. Even if you think this is a kind of a valuable thing to do, you have issues where multiple clients can be behind the same IP address quite often, and you essentially are sharing fate with everyone who's at your house or at the cafe you're at. You can hit limits. But worse than that, being able to track the IP address over time is a privacy violation, and it's a tracking vector often. So there are a lot of great privacy services, VPNs, Tor, and at Apple recently we've released our private relay service, which has 2 proxies in between your client traffic. And it's all about trying to improve client privacy by having your client identification be something that's explicit and not just passively gathered up by looking at your IP addresses. But as you'll note, this does take away some of the capabilities of origins to do correct rate limiting, or any type of inference of client state, because they don't know the IP address anymore. They don't know how to do this. And this is what the entire ecosystem was built upon for a lot of things. So private access tokens is about figuring out how do we let things like rate limits work regardless of IP address. But we don't want to do this by introducing a new stable identifier that's going to hurt privacy. We want something that is privacy preserving but lets you prove something about your access patterns. And so where is this useful? It's certainly not for everything. This is about cases where you have anonymous access that you want to be able to prove some limited client state to do things like per origin rate limiting. And this is not for any case where you're going to log in anyway. That's a much stronger identity, and that should be solved elsewhere. And to help us think about this, I want to split kind of the world into 3 categories here. On one hand, in this green box on the left, we have things that are truly anonymous access that don't need any state. It's inappropriate for them to have any client identifiers. I just want to be able to read a Wikipedia article. I just want to use a search engine. Public resources, no need to track me on that. On the right side in the orange box, we have things that legitimately should have authenticated access. If I'm going to upload something to my own social media account, you should probably know who I am, and I should probably log in. So the question is, there's this category in the middle, which is something where I'm coming in with an anonymous access. I haven't logged into anything, but you do want still some minimal per client state, such as rate limiting. As we mentioned before, this can be accessing some a bit more privileged resource, like being able to read a newspaper article that otherwise would require you to pay, but they're trying to let you see some things. But also this applies for account creation, where something wants to make sure that you're not having 1,000 different accesses from a bot trying to create 1,000 new accounts, or even if I'm doing login to a site where I'm anonymous before because I haven't logged in yet. A failed login is something that you probably want to rate limit so that someone's not just trying to brute force a password in. And so these are cases that have been built up around doing IP address rate limiting today. They exist, and they're going to need to do something as connections get more and more private. And the concern is that if there is not a good privacy preserving solution, use cases that are in that middle box are going to have to move to one side or the other. Either they're going to say, great, we're just going to go totally open, and that's fine. But we're concerned that there are going to be more things also that would move more towards the right to say, okay, if you want to read this, now you need to sign in with this major social media network to be able to get into something. Or, hey, if you want to create an account with us or log in, you need to bootstrap it with some other account of some major service that we trust. And that's going to be worse and worse for privacy. So we think that there is a need to solve this. And private access tokens is about solving this case. Essentially, it allows the client to prove to an origin that it has performed fewer than n accesses in a time window. And that's all it's going to prove. And the key thing that we have as a requirement in here is we want to make sure that no entity in the system can correlate user identity with their browsing history because of this. All right. So how does the protocol work? There are two parts to it. There's a token challenge request, and then there is an issuance protocol. So the challenge and request, quite simple. What we're proposing here is just have a new HTTP authentication method. You get a challenge. Essentially asking the client, hey, you're trying to do some privileged operation. You're trying to create a new account. You're trying to read the newspaper article. You need a token to get this, or otherwise, you'll fall back to something like getting the CAPTCHA or having to do some other type of proof. So the origins can challenge for this, and then the clients will asynchronously fetch an unlinkable token that's specific to that origin and then present it, and then the origin can validate that without having to do any more work. This is a publicly verifiable thing. So how do we actually get the tokens? So in order to go through this, I want to kind of build up why we have the architecture we do based on showing you kind of process of elimination that you can't do some other architectures. Clearly, we're not going to be able to just fetch the token from the origin itself, because kind of by definition in the assumptions here, we either don't want to log into this origin provided our real identity so it can track us, or we can't because we don't have an account yet. So that's not a good option. So we could bootstrap off of something that you could call like a token issuer. And you could imagine I could have some issuer that can validate me, can know that I'm a real device or have an account that I have, and then on my behalf get a token for that origin that I can then present to the origin I want to go to. And this would technically work. However, this doesn't meet the goals we have for privacy, because this issuer would be in too privileged of a position, because it would be able to identify the clients and track their state potentially, as well as knowing all the origins that they're going to. And this would allow them to learn the browsing history and be a bad privacy story. All right, so we end up with a bit more split model. If you've gone to Oblivious HTTP, this type of split is not the first time you've seen this. So the model that we're proposing here is that you have a separated mediator and an issuer. And a mediator is something that's chosen by a client that is able to authenticate the client and validate who the client is, but is not able to see what they're trying to access. But it helps just kind of mediate this entire transaction and represent their validity. It will forward blinded requests for tokens to an issuer. Issuers are chosen by origins as entities that can vend out tokens on their behalf and enforce the policies that they want, such as you get no more than 100 tokens per hour or even 5 tokens per week. So overall, the protocol looks like you have this end-to-end challenge and response between the client and the origin. And in between, you can have these little loops between the client, mediator, and issuer to actually grab new tokens. Now, the clients never tell the mediator what the actual origin name is. They only tell some pseudonym, an anonymous origin. The actual origin name is encrypted from the client to the issuers. The mediators are responsible for keeping account of tokens that are issued to each client for a specific anonymous origin within a window. And the window is something that the issuer can define to essentially say, hey, I care about rate limiting things within an hour. Like you could only try to create an account 5 times in an hour, or you can only have 5 failed logins in an hour. And that policy window is given back, is told to the mediator to help the whole system work like this. There are, I just want to briefly mention some of the cryptographic dependencies that we have for the protocol. For the origins, it's very, very simple. They just have to do a verification of an RSA blind signature token. They don't have to do any double spend prevention. They can just validate that the token looks good. On the issuance side, the system of the client, mediator, and issuer do need to do a bit more work. They use RSA blind signatures for the tokens themselves. The client uses HPKE to encrypt the actual origin name to the issuer. And then the system also uses a blind Diffie-Hellman with a Schnorr proof of knowledge to help the mediator prove that the client is not lying about the mapping between its anonymous origin and the actual origin name. Chris will be talking about that in CFRG for the crypto details if you're interested. All right, so we've talked about why we think this is important to solve. We've talked about what the basic architecture is. But the last thing I want to hit on, which is I think one of the most interesting parts, is the kind of deployment model. So I mentioned some of this already, but the clients are responsible for choosing their trusted mediators. These are people who they're willing to log in with or who have some notion of client identity anyway, that they know isn't going to learn about their browsing history, but can help them as they want to get tokens. And this could be based on a number of different things that's not specified in the document. It could be based on a device level built-in hardware cert. It could be some verified account that you have with a service, some two-factor thing. Origins are responsible for choosing trusted issuers. And one of the assumptions of the architecture is that each issuer should be serving multiple origins. That's required so that the mediator doesn't learn based on going to an issuer exactly what website you're going to. And this would work really well for issuers to be existing CDNs or web hosting services or any kind of security captcha service that you have. It could be a number of different things, but different entities that would be representing origins. And then the system does rely on the fact that there needs to be some level of mutual trust between the entities running mediators and the entities running issuers. For privacy reasons, they should be different entities, and the client can essentially, do some level of knowledge because they are choosing what mediator they go through, that it's not the same thing as the origin that they're going to or the issuer that they're using. But if trust does break down, if mediators start lying or doing, letting clients get away with too much, then you could imagine that there wouldn't be good support between mediators and issuers. So they do need to live up to a certain standard. So one way to look at the architecture is that you have many different clients behind single mediators, many different origins behind single issuers, and that is kind of what preserves and protects the identities of clients and origins from the other parties in the system so that there's no tracking here. Briefly talking about client identity, this is something that is determined by the mediator, really. The private access tokens architecture does not require just one mechanism for this. This is something that we can imagine could evolve, but really just needs to be something that the ecosystem agrees is hard to forge. It shouldn't just be, oh, you have this IP address. It needs to be something that's relatively hard to get, so one client couldn't just get 1,000 different identities very easily. But users could definitely legitimately have a few identities. I may have different devices that, if I'm using device level authentication, those would look like different things. You could also imagine that different applications or different browsers on a single device could use different accounts as their root of trust. But effectively, the amount I'd be able to multiply my effect in the system would be maybe 1, 2, or 3 times, not thousands of times, to be able to fool a system. And then lastly, the thing I want to touch upon for deployment is how we avoid centralization in the system. It's definitely something that we are conscious of and want to avoid. So the mediators and the issuers, kind of by definition, are entities that are helping represent many different clients and origins. So there are fewer mediators and issuers than clients and origins. That is important, but we should also be avoiding letting the overall ecosystem just have a handful of these that are just kind of the big players that it's impossible to get in. It needs to be easy for new mediators and issuers to enter the overall ecosystem. And you particularly want to avoid situations where issuers who are kind of working on behalf of origins only allow a specific mediator to essentially force clients to have a particular type of trust in order to be able to use different origins. So, you know, this is not an easy problem to solve. It's the type of thing that is difficult to solve at a protocol level. But we believe that, you know, private access tokens may actually be able to have less centralization problems than other alternatives when you think about the overall ecosystem. So looking at some of the kind of comparisons, as I mentioned before, if we don't have a good solution in this space, we'll see, and we already do see a lot of things moving towards, oh, a sign in with blah, where blah is some large company. And these are things that origins choose to prefer and choose to partner with, and they can essentially embed some relationship with another site that will be more likely to have a user account already. And they could be sharing data on the back end. You really don't know what they're doing, and this is potentially a big privacy problem. And so without an alternative for clients to use, if we're trying to move away from CAPTCHAs and if we have more private IPs and stuff, we could see things moving towards this. And this being a per origin choice is something that would be really hard to move. And we're not going to end up with a situation where we're going to have sign in with 50 different services and every little guy is going to get in there. Another comparison to make is the existing proposals like Privacy Pass. So I'll mention a bit more later, but Privacy Pass is something that allows a client to present a token to one origin that it got from another origin that it was able to get some bag of tokens for that's not origin specific. And in this case, the origins that are redeeming this can choose to discriminate based on where the tokens came from. And so they could also be in a situation where individual origins could choose to prefer major services or choose a small set of token vendors that they trust. With private access tokens, overall, yes, there is that general risk, but it's important to note that the origins don't get to see the mediators. They're only doing this through the issuers that they work with. So origins cannot individually discriminate based on how the client authenticated. They have actually no way of knowing how the client authenticated or what type of device or what type of account they had. So it's actually a better privacy thing here. Now, you could have a situation where issuers start rejecting new mediators. Since mediators and issuers are all talking to each other, there's not really paired in any way. They are going to be a kind of a globally known list, and this is something that could be publicly reported and publicly audited if there starts to be blockages between any of them. Now, sometimes this could be legitimate, like you could have a mediator that starts cheating and lying on behalf of its clients, and in that case, yeah, the ecosystem should decide to reject them in the same way that you can stop trusting a given certificate authority if it stops behaving correctly around how it signs certificates. So this, we think, is the type of architecture you would end up with, and we think they could have the right incentives to move this forward. And I do see someone in the queue, but I'll just quickly finish my slides. I only have 2 more. So anyway, we have the question about where this work should be done. I do want to point out that there is a lot of related work within Privacy Pass. So private access tokens is very similar in many ways to Privacy Pass, but it has some key differences from what Privacy Pass is currently working on. First, it does involve some per client and per origin state. It's not allowing just unlimited access. And we believe this is actually something that makes it much more attractive and more useful for cases that want to be able to replace IP address as a rate limiting mechanism. If you don't have that ability, you still have to fall back on something like IP address to allow you to do the rate limiting. These are also tokens that get scoped to a specific origin, so you don't have any problems about cross-origin spending or a case where one origin can end up essentially consuming your entire bucket of tokens and you have no more tokens left for other origins that you prefer to use it with. It is using a private access tokens use a challenge, so it's an online protocol, and so this doesn't allow you to do the same type of token hoarding that you could with Privacy Pass, in which you could actually get passes from many different clients and just hold on to them, and then spend them and make it look like you're legitimate when you're not. And lastly, we are defining this as a publicly verifiable token, so it doesn't require the origin to do any work of talking to the backend or the original token issuer to prove that it's a valid token. So in some ways, we think this could be a more generic form and potentially a more useful form of Privacy Pass. All right, so our question essentially is, well, first, what do people think? But then if this work should it be done as something like extending the work that Privacy Pass does? Should it be something short-lived in a very specific working group, or something else? And that is all I have. PHP.
Yeah, I like this a lot. There's just one slight problem. I proposed something very similar back in 2003, and VeriSign has a patent on it. So it's not a very problematic patent. It was filed March 25th, 2003. But that is something to bear in mind. The other thing is that what I was doing at the time was I got very upset about proof of work, which I believe is an absolutely appalling proposal. I thought it then, I think it now. And the claims are very broad. It's not just for trusted computing implementations, but the main idea was put this in a trusted module on the device.
I see.
And then you can get rid of all your other requirement. All your mediating parties go into the device. It might be that in the current circumstances, probably the only thing that VeriSign could do to get some value out of that patent at this point would be to make some agreement with Google. If you could get Google and Apple involved, they control silicon, and they could get it pushed into the hardware.
Yeah, and certainly you can imagine the mediator could end up in the hardware of the client itself.
Yeah, it would be very, very easy thing to add to anything that's got a secure enclave already.
Yep.
I mean, the reason it didn't happen 10 years ago was that there was another patent prior to mine that stopped it happening that we could never get access to. So,
So all right, well, thank you for the heads up on that.
Yeah, I'll file the IPR or tell Bert or whatever to do it.
Okay, thank you. All right, Ben.
Hi, Ben Schwartz. I happen to be one of the chairs of Privacy Pass.
Yes.
I think that this work is appropriate for the Privacy Pass working group.
Okay.
I would be happy to see it come there. I don't think that there's any presumption that we would essentially take this work as is and add it as a new working group work item. I think that these use cases are important and that we should think about making sure that we satisfy the use cases that are most prominent here. And that may mean changing what the Privacy Pass working group is working on. I don't think that we should essentially forge ahead with both this and something that looks like the current Privacy Pass protocol in parallel. I think we should essentially look at the elements of these, look at the requirements, and come up with one solution to pursue first, at least, and let it roll out and get some experience with it before we attempt to do another permutation of the same ingredients for a similar purpose.
Right. Yeah, and just speaking to that briefly, we have both Chris Wood and Stephen Valdez, who are Privacy Pass authors, working on this, and I think there is an appetite to, even if long-term, some of the use cases could involve different flavors of tokens to make a lot of the stuff like the token challenging and requesting and issuance compatible, and maybe just have, oh, I want this type of token, or I have that type of token.
Yeah, one thing I think we need to consider is that there are going to be mixed ecosystems. If we have multiple of these things, no matter whether in parallel or sequentially, we're going to end up with mixed ecosystems, which means we need a negotiation system, a capability of negotiation to identify which kinds of tokens both parties possess, which means we need to think about the entropy leakage, the privacy reduction that is revealed by which of these kinds of tokens you actually support or possess at the moment. Which means we need a unified privacy analysis. I think those are all reasons to take this to the Privacy Pass working group.
Great, that makes sense to me.
As an individual, I have to say I don't find this as compelling as Privacy Pass today. In particular, it seems to me that this architecture has much more complicated trust relationships required between the various parties, whereas Privacy Pass manages to achieve, it seems to me, very similar security and performance results with much less reliance on tricky partial trust relationships between the parties. So I think that we should try to essentially lean toward computational privacy and away from information theoretic privacy to the extent that we're able. And Privacy Pass, as currently formulated, I think gets us a little closer. Also, I think there's more similarity here than we let on, because both of these protocols have certain assumptions baked into them that we are not particularly talking about. For example, having a huge number of issuers here would get you back into the Privacy Pass problem of essentially leaking one bit of information for every issuer that is or is not present on the client, and so that means that they share the same privacy consideration there.
Ben, as much as I hate to disrupt the technical conversation, let's end it here. And for all others who are on the queue, so the queue is closed, and please keep it brief. And we would most importantly like to hear your feedback on how to dispatch this.
Okay. Just one thing to reply briefly, Ben. I agree that is desirable to have something simple with simple trust relationships. I think the main issue we see with the current Privacy Pass is that it is simple, but it also offers sufficiently little information, low value to the origins, that it's actually not useful for replacing a lot of the cases that would have CAPTCHAs or would have other types of rate limiting today. So we want to just increase the utility. All right, Siobhan? Oh, your audio. Oh, can I try talking now? Or...
Is that better?
Yes, that's much better.
Okay, great. Turns out my headphones don't work. So yeah, I was just wondering, it reads like the presentation kind of read like privacy preserving rate limiting, but the draft mentioned geofencing as well. And I saw that there was a client hints proposal as well in the GitHub repository. And just wondering, was a reason for that? And I guess just quickly, the other thing was, it seems like there's a centralization concern around, especially the mediators. So there might be worth having some discussion about that in the draft.
Yeah. So yes, there are, and the draft mentions, and we believe, the overall architecture could allow you to have other bits of information other than rate limiting, like you could use this, or you really use kind of any privacy pass type ecosystem to sign or verify that, oh yeah, you came from this country or whatever, and we know something about the client that way. So there are other bits of information. We don't want to get into the complexity here in this talk. What was the second part of your?
Just a comment that we should probably talk about the centralization concerns with mediators, especially. I think.
Yeah, and yeah, we should discuss that more in the draft. As I mentioned here, I think largely it does degenerate to a lot of other cases where essentially if an origin can know where your kind of sign in or where your root of trust is coming from, then it could similarly end up favoring just few large actors, and hopefully we can actually find a way to make this better than those. Thank you.
Ipr, go ahead.
Hi, Tommy. Thanks for presenting this.
Hello.
So I think, I'll hit the dispatch question first, but I do want to talk about the technology for a moment. So I think this isn't quite ready to go. Honestly, I think there's a bunch of questions about what the actual problem which you're trying to solve is. I do agree with Ben that having this and privacy pass together is like bad news. So we should try to figure out, what the IETF is going to do in the spaces. So I think we really first need to get agreement on the use cases. You listed a number of them, but like quite a complicated system, and the complexity all derives from the desire to have a rate limit on a specific client for a specific origin. And all the other cases you have are largely about like making assertions about the client in particular, but not about the origin specifically. And so all those can be solved with a privacy pass solution. Do not need any of this complicated, stuff having to do with the mediator and the issuer. So I think it's really important to determine whether we think that's enough of an important use case to motivate an effort in the space. And I guess you're probably getting from like what I'm saying that I'm not persuaded.
Yeah. Can you explain why they are not origin related? That essentially having a global pool of rate limiting for everything I do would satisfy these cases?
Well, no, what I'm saying is geo. Geo has anything to do with the server. Is a human, does that have anything to do with the server?
Nope. And that's not what we're talking about here.
Okay, but you do list them. So like, I think, but you hear about captchas, right? The point of a captcha is to demonstrate the person as a human. And so when you sort of say, oh, the alternative is captchas, well, the alternative, this is not captchas. The alternative privacy pass is captchas.
I think we often see that captchas will come once we have hit rate limits, or once people can prove, or once they do not know if you have been below some rate limit. And so avoiding the captcha can also be
I guess I don't think it's a requirement.
Anyway, yeah.
Sorry, we are eating into the next presentation's time, so keep it brief. I see, Ipr, your recommendation is not to dispatch it to privacy pass yet, or should it be presented there and it can be discussed how to iron it out? Is that the recommendation?
What I would like to see is a more concrete analysis of the use cases and which ones can be addressed with require technology that's fancy and which ones do not, and then we can decide whether we think those use cases are sufficiently important to solve to pay the price of the complexity and the potential choke point effect that this creates. And I guess I do think it's important to mention this choke point effect, because I think it was mentioned previously, that we do have a worked example of this in the identity system, and we have basically two identity providers. So, and I don't think it's at all implausible that origins will insist that I see that the issuer only trusts Google and Facebook and Apple, and that would not be a desirable outcome.
I agree.
Okay, Andrew, keep it brief.
Yep, I'll be very brief, but just two quick technical points to echo the discussion from yesterday in a different working group. I think this app really does need to address, before it does go forward, how to avoid the problem of colluding mediators and issuers, because if that's not addressed, the benefit it's providing is completely illusory. And in fact probably unhelpful, because it potentially implies it's giving more privacy when it's actually giving less. And I think that from an end user point of view, that's dangerous. if that happens. Also, I completely agree with Philip about the absolute sort of appalling use of proof of work, just as a general principle. That absolutely should be avoided. In terms of answering the dispatch question, privacy pass seems like the obvious place, and I think, as somebody just suggested in the chat, maybe have it looked at in more depth in privacy pass, and then if need be come back to dispatch after a deeper look with more time would be my suggestion. Thanks.
Sounds good.
Okay. Question to ADs and co-chairs: what's the dispatch decision here? I think you have been following the chat more than I have, but is dispatch to privacy pass the correct decision here?
Yeah, there's been some proposals at the mic here and some discussion in the Jabber channel. So it looks like that there's fairly good energy behind dispatching this to privacy pass. Having some detailed discussion there about how to kind of mesh this with the use cases and technology that privacy pass has. And if anything like net new comes out of that, I think we can take it up here again. But I think to first order, dispatching to privacy pass is the outcome here.
Sounds good.
Thank you.
Yeah, so just to follow up on what kind of Richard said, it really does look like the expertise to have this conversation is in privacy pass. So I think if we're going to decide is this privacy pass plus this work, privacy pass becomes this work, use cases from this inform kind of privacy pass, all the arrows kind of point back to the nexus of privacy pass. So let's continue the conversation there. I would remind the community we still have two potential angles out of that. If we need to change privacy pass, that's a recharter opportunity. So that's another place for us to kind of talk about whether we're comfortable with what the scope is, if there is a scope change. And then if it turns out that the kind of discussion from privacy pass says this is different, again, I'm kind of purely speculating here. As others have suggested, that speaks to another turn through SecDispatch then. Thanks.
Okay, dispatch to privacy pass in that case. Thanks, Tommy. Jake, I guess you're presenting. I shared your slides already. Hope that's fine. Should we start?
Thank you. Yep.
Okay.
Okay, great. Thanks for the time here. I'll be talking about multicast security and privacy considerations. Next slide, please. So the problem we're trying to solve is scalable delivery, multicast, of course. The thing that we don't know another way to solve, and the reason we're focusing on multicast, is the congestion we observe at ISP access layers. This is essentially a broadcast medium, and so sending a single packet across it for all the duplicated traffic that drives the peak loads that are observed at ISPs is something that could be avoided if we could make use of multicast. And we see a fairly large gap. I discussed this. There's a link to the BARBOF at IETF111 where I went into a bit more detail about this later in the deck. There are other impacts to end users that we believe can be addressed in the same way. The capital costs are driven by the peak load. This is both for the sort of content owner, content distribution network, and for the ISPs, and these costs pass all the way through to end users and have a disproportionate effect on those who can afford it less. And the peaks are generally driven by the popular content. These big game downloads, the big sporting events that everybody wants to watch at the same time. And that's the main thing we're trying to address. And the problem keeps getting worse. We can go into more detail on that, but the motivations, I think, are clear. There's a few things that that people often react to, like, do we really have to do something as hard as multicast? We have looked at peer-to-peer for this, and of course that doesn't address the ISP access congestion problem. It in fact makes it worse, and the ISPs are firmly against it, as opposed to multicast, where, as you'll see in a few moments, they're tend to agree it makes sense. application level multicast also doesn't address that access layer problem, although it does help address some of the other problems. This is essentially what CDNs do already, and we're finding that there's a substantial gap that we would really love to see addressed. So next slide, please. We've been working on this at IETF already, primarily in the MBOND working group. The reason that we did it in this order, that we haven't come to security really before, is about sort of figuring out how viable it's going to be. Are we really going to be able to get this stuff delivered? But we started with dozens of informal conversations bouncing the idea around over the course of several IETFs, with particularly with a number of browser implementers, just in private discussions, seeing if there's any obvious stoppers that would make it clearly impossible. Everybody agreed there are challenges, but that with sort of sufficient buy-in, this could be reasonable. So we went ahead and we made the pieces that we think would be necessary. We had some proof of concept implementations done at hackathons. Have been reporting on it at MBOND. There's all these adopted drafts in MBOND. And at the last IETF, we ran a barb-off and got what feedback we could from that. And now we're trying to sort of follow up on the next steps here. Next slide, please. In addition to our IETF work, we've been doing a bunch of outreach outside the IETF. We've had a bunch of ISP conversations. We consider that kind of the critical feedback, because there's no point if this stuff won't get delivered. But the answer we've gotten has been largely positive. We've likewise been talking to a bunch of the content owner customers we have about whether this is feasible from their side, and likewise the answer is mostly yes. We did several lab trials with ISPs, where the ISP gear was being used to do the multicast forwarding based on ingesting according to the architecture we're proposing, using AMT and Dryad. References there. So the feedback we got from the ISPs was that in some cases there were problems. All the problems we encountered were possible to work around by changing the addressing. So we made a draft about how to do that. This also has been adopted by MBOND. And so with that, we think we've covered the sort of practical problems to getting this potentially delivered. And we'd like to move forward with the problems of how to do this in a useful way at the application layers. We're looking into both web and non-web traffic, primarily because the peaks that we have are driven by both of these cases, the peak traffic loads. But the web traffic is one of the places where we're going to be blocked if we can't get into browsers. And in order to get into browsers, we need to have a decent security model. And there are differences between the way multicast security would work and the way unicast security has worked up till now. So this is why we tried to cover these considerations in the draft that I hope people got a chance to read. There's some other implementation work here. We've got a W3C community group that's chartered to try to incubate the work. I'm chair of that. There's a demo API just sort of proving the viability of playing video using, and this is by the way a port of a receiver that we have as part of a multicast product. That's a walled garden multicast TV delivery product. But we've got that running under WebAssembly and playing video in our own build of a browser. We gave an intent to experiment into Chromium, and we got some feedback from them. The feedback is kind of what drove the writing of this draft, because the point that was made is that we have to have confidentiality as part of the design, which it was not up until that feedback came in. We get into some of the reasons why that is the case in the draft, but basically it was a convincing position, and so we've taken it on board, and we're trying to grapple with the complexities that opens. That's the sort of background of the genesis of this draft. We are starting in the community group with aiming to integrate to web transport, and that's so that we can. The idea there is that you can take existing multicast applications. If you can solve the fundamental security problems that we do outline in the draft and sort of get an acceptable use case, then web transport would be a great fit and would allow, in the way that we've already done, sort of adapting existing multicast applications into a browser context and deploying them at scale, and then would open up experimentation for other APIs that would also be useful. Yeah, next slide, please. So the problems that we want to address here, we want to separate the integrity and authenticity from the confidentiality concerns, because these are kind of driven by different threat models. It's very important to prevent someone from inserting a packet of death that's accepted and uses the rendering bug to take over all the devices of people watching the Super Bowl or whatever. It is likewise very important to protect confidentiality, but this is kind of a different set of problems. And there's some trade-offs here that we try to get into in the draft that come from the fact that with multicast, you have the same exact packets that have to be decoded by many different receivers. This inherently creates a sort of, content discoverability problem of some sort, but that comes with the removal of the destination IP address, which increases anonymity at all the network locations that are just, increasingly distant from the end user that's receiving it. We tried to look into like what are the threat models about here, and for confidentiality, most of what's written down covers like personalized information, things like your medical records or your bank account info, and it's on top of that, the traffic analysis discovery is pretty good at picking out the especially popular things. So we think this doesn't open up particularly new stuff, but that is a point for discussion. If this really does create an unsolvable hole, then we need to know about it and stop working on it. But our position is basically that the alternatives are just as bad, perhaps worse, for the scalable traffic that we're actually seeing. And so we think this is still worth pursuing in spite of the sort of differences in the security model. We're trying to get that all articulated, and this is a big part of the work that we anticipate doing. Next slide, please. So the existing work starts with the multicast security draft you saw. We have an adopted draft in MBOND that would benefit from a better security expertise. This was originally argued as being reasonable to include in MBOND based on like it doesn't do any novel crypto anything, and I would argue that if there were a multicast focused security place, it would have a better home there because it really does need some security expertise looking at it. There are other pieces of this that are likely to also require documents going forward. I've listed the ones here. As I said, we're trying to target web transport. So documenting exactly how that's going to work. These experiments are just beginning, but going forward, we would anticipate writing the appropriate documents to include it and incorporating all the great feedback and useful insights that we get from reviewing the actual security requirements and considerations that we've tried to put forth in the multicast security draft. And there may be, going forward into the other APIs, some other related work that we'd want to address as well, including specifically which protocols would be supported by browsers and how it would all work for handling APIs like fetch or download. So in terms of getting into browsers, this is, we're basically blocked on progress until we can get a firmer consensus answer, or at least a firmer tentative consensus answer on what needs to happen in order for multicast to be used safely on the internet with the sort of modern threat model for the internet. And I think we're really missing a lot of security expert participation in this space at this time. So that's basically why I'm here today. Next slide, please. So my first question is whether this is suitable for IETF work, and if so, what should we do with it precisely? You know, I have a few ideas here, one of which is reopen MSEC. That was a possibly with a recharter that seemed like a pretty good fit for this kind of thing. Maybe a separate thing for broadcast MSEC, but I would welcome suggestions and feedback on what we're doing here and whether anybody can usefully comment. So with that, I will open the floor to questions, comments.
So before we let others weigh in, we have like 9 minutes left, and we have the option of overflowing on Thursday. Of course, I would personally prefer to get a dispatch decision already today, but go ahead. The queue is open. Ben?
So I guess the question I have is to try and get clarity on what questions you want to answer as the next steps. So like I heard a fair bit about like the question being, is there a security model or security framework that we can use that would make multicast traffic compatible with like traffic in the web to the browser? Is that sort of what you see as the key question to be answered here?
I would say with delivering it safely to end users, I think there's a lot of multicast traffic today that goes to end users that is not a part of the web security model, and we can start there, certainly. Like we can do some multicast based delivery on some of our use cases, like some of the game delivery pieces or software updates, and as well as potentially like there's some interested parties with that have kind of large footprints of those like smart TV on a stick kinds of things that you can plug into the HDMI cable on your TV or whatever, and these can go ahead and start deploying multicast. So we can address some of our use cases today, but we do think that web security is an important part of this and a big part of the security question. And we think that these same security questions are applicable to these other domains as well as the currently widely used multicast delivery for TV that's operated by MSPs. So we'd like to address all of these questions and land on a sort of as safe as it can be for end users under specifically what considerations that are properly written down, and to apply that to all of our solutions. If the answer is, well, you have to get some deployment first, then, I mean, we are intending to do that to the best of our ability, but browsers are going to be a big part of solving the ultimate problem of scalability that we need. Yeah.
Okay, so still like looking at a security model, but maybe I was too narrow in the initial statement.
Yeah, I mean, web doesn't have to be the starting point, but I think it's one of the more complex spaces, and so it's one of the ones we want to get the conversation started on today because we think we're going to land there. Yeah. Ecker, hi. Oh, and thank you, Ecker, for your feedback on the list. Really appreciate the conversation there.
Thank you. Yeah, I mean, I think it is a dispatch question. I think I don't know where to take this. I guess I'm not sure your problem is quite the problem you think it is. Which is, I mean, I guess like I did read that message that Chris Palmer wrote you, and I guess what I would say is if Chrome were really enthusiastic about this, then you would have got a different message, and it wouldn't have said like solve the problem for me, and then I'll be interested. So I think your problem is not necessarily about security. So I think probably like trying. I guess I would say like there really are two web security models. One is the one that's sort of implied by web transport WebRTC, and there was the one that's implied by fetch. And as they fetch is the origin model, and web transport WebRTC is something quite different. I do not think there's like any near future chance of like having this somehow mapped into the true web origin security model. Things are just too different, and we spent so many years trying to reason about that and only barely understand it now that I just like think that's extremely unlikely that people are going to put the effort into it. Maybe there's some version that maps into like the web transfer web RTC model, which is like not really tied to origins, because that's a much simpler kind of case. But I guess, I guess I would say like the IETF is probably not the place to think about that at some level, because the security properties, the actual security properties technically provided here are not that complicated. What's complicated is mapping into the web. So I'm not quite sure what to do about that. It's almost a WCC question rather than an IETF question.
Yeah, well, thanks. We are certainly engaging with W3C as well. We've opened the discussion with Web Transport in particular, and Web Networks interest group has taken some of this on. It maps well with some of the sustainability work that's starting there, but we do want to get the conversation underway. I mean, you're kind of right about Chromium. They're not interested, but my read is that they're not interested because they're skeptical it will end up working. I think a lot of people have that skepticism, and Multicast has a history that certainly justifies it. But we do think this problem needs solving, and this is a really good way to do it, and that the problems do not look fundamentally unsolvable. So that to the extent that we can continue gaining traction and get some forward progress on this, I don't think it's really as out of reach as people think it is. But I do acknowledge that remains to be seen. But thanks for the feedback there.
Watson?
Cloudflare, it's not clear from my presentation whether or not you need a protocol to meet security properties you have a good idea about, or don't really have an idea of what the security properties are you need to meet. And I agree with Ecker that if you don't know what security properties you need to meet, that's sort of a W3C thing, versus coming up with a protocol to meet them that works in Multicast, which might be more of an IETF thing.
So we have some idea. We think that the draft we put forth about security considerations presents a model that we invite criticism on, and we'd like to sort of hash out to everyone's satisfaction. The feedback we see from W3C is that, well, obviously this has to have the underpinnings of protocols that satisfy the web security model needs, and so this is the sort of middle ground we're stuck in at the moment. And if we can get some forward progress on agreeing with the security model, get some feedback on what that's doing, then as we go ahead with trying to build the protocols that meet that security model, then we'll have some confidence that it's actually driving in the right direction. That's kind of the way we're looking at this now. It's got a lot of moving pieces and a lot of people involved, absolutely, but
Ben,
if you've got a better idea what we should do, please.
We have like 2 minutes left, so Ben, keep it very short.
Hi. I think that this piece of work is too big to do all at once. I think that the first step would be to solve the protocol problem and leave the browsers out of it, basically. And I think there is a logical way to do that. And my suggestion would be to dispatch to CDNI and treat this as a CDN to CDN multicast use case, where you're moving content, where you're essentially standardizing a component of application layer multicast. So
yeah, that I believe is useless to us. So.
Client is a cache box, and then we can come back to the question of how to move that cache closer and closer to the client.
Wow. So we believe that problem is already solved and irrelevant to this case. So at least that's my belief. So thanks for the feedback. I don't think it's viable.
I think we have to stop here, and we need to come to some sort of consensus on what's the best way to dispatch this. What I saw on the list, and I received some chats, people seem to be saying we are not sure at this moment, but perhaps discussing this on a mailing list seems sensible. Would it make sense to dispatch this to a mailing list, say MSEC, or starting a new mailing list? That depends on the ADs and the authors who are driving this. So how about we we continue the discussion on a list once there is enough traction and we have more clarity whether this is CDN to CDN, whether browser should be included in the first attempt or not, will result from the discussion on that mailing list, and it's up to the ADs and you which mailing list this discussion happens on. We'll obviously inform on SecDispatch for those who are interested in continuing this discussion. How does that sound? ADs, is that okay?
That sounds like a great plan. So, Jake, if you want to kind of reach out, we can talk about whether a new mailing list makes sense or MSEC.
Okay. That is a start. Thank you very much.
So we are right at the hour. I think I'll just summarize the two dispatch decisions. For multicast security, the discussions will continue on a mailing list. For private access tokens, we have tentatively dispatched it to Privacy Pass, and the working group needs to make a decision on whether it needs to recharter, update new use cases, or send it back to SecDispatch, and we'll see about that. So I guess with that, we have managed to cover both the drafts in this session itself, and we won't need the extra time on Thursday. Thank you for joining. I guess we are done for today. Am I forgetting something? Looks like not. So, okay, have a good rest of the day ahead.
Thanks, Mohit.